In this video, we're going to introduce the topic of bomb calorimetry. Bomb calorimetry is a little bit different than the type of calorimetry we've seen in previous videos where we had our coffee cup or simple calorimeters. Now, this setup over here, which is shown, is a bomb calorimeter. And the main difference is that we have these ignition wires, which are connected to our sample inside of this reaction chamber here. And we actually are going to combust or blow up kind of our sample here and then measure the temperature change in the water in the surroundings. So we see there's still stirring, there's still a thermometer to measure temperature, but what's really being measured here is not going to be the enthalpy change, but the delta E, because the volume is going to be constant in this setup instead of the pressure like we saw before when delta H was equal to Q. So here our Q of reaction has a slightly different equation. So now for bomb calorimetry, we use the heat capacity of the calorimeter and the change in temperature to calculate the Q of the reaction. So let's see if we can do that for this example here. So we see that we have 0.5865 grams of a sample of lactic acid, and that's the structure here for lactic acid. That's going to be burned in a bomb calorimeter, and we're given the heat capacity over here in kilojoules per Celsius of our bomb calorimeter, so 4.182. And we're told that the temperature increases when that mass is combusted from 23.1 degrees Celsius to 24.95. So we're asked to calculate our heat of combustion, so our Q value, Q of reaction, for our lactic acid in both the units of gram and moles. So let's take a look here and see how we can do that. So we know that our Q of reaction, as mentioned above, is going to be the negative heat capacity of the calorimeter times delta T. So if we plug in negative 4.182 kilojoules per degree Celsius times our delta T, so that's going to be our final 24.95 minus our initial temperature, 23.10. So that's going to be 1.85 that we plug in there. And then we're going to set that equal to our Q of reaction. So for this, we're going to end up with, this is not given per mole. Rather, if we want to solve per gram, we can plug in this value. We're going to get about negative 8.902 kilojoules, and then we can divide by our 0.5865 grams, and that will give me my Q of reaction in the unit of kilojoules per gram of 15.2 kJ per G. And if I wanted to convert this to moles, first I would have to take my mass, 0.5865 grams, and divide by the molar mass of lactic acid. So I would use my periodic table, do 3 times carbon plus 6 times hydrogen plus 3 oxygen. So I get about 90 grams per 1 mole. When I divide, I see that I have about 0.006517 moles. So what I can do is I can take that negative 0.8902 that I got over here and divide that by my number of moles now, 0.006517 moles. And this will give me my units of kilojoules per mole and a value of 1,370.